In this video, we're going to show how to construct finite difference approximations to partial derivatives of a 2D field defined on a discrete set of mesh points. We're going to do this in Matlab using the shift operators that I presented in the previous video. We define four matrices, sparse matrices, IE, IW, IN, and IS. And what these matrix operators do is they take a 2D mesh of points which have been converted into one long vector, and they reference the point to the east, that's I east, the point to the west, IW, the point to the north, IN, and the point to the south, IS. And we're going to use that to create finite differences by taking differences of these operators. So the I matrix over here, that's just the identity matrix. So it's like multiplying by 1. If you multiply I times a field, you get back the original field. So I doesn't do anything when it acts on a field. All right, so let's do the finite differences. Finite difference operators. So if we want to do a partial derivative with respect to x, we can approximate that by taking the difference between two neighboring points on the mesh and then divide by the delta x, the spacing. So two neighboring points in the x direction. So we can do that in two different ways. We can reference the point ahead of us in the positive x direction and subtract the present point, or we can take the present point and subtract the point in the negative x direction. And those two approximations are valid approximations to a partial derivative. So if we do the forward one, f dx, that's the same thing as looking ahead. We get that by multiplying the field by IE, and to get the local point, we just subtract the identity. And then we have to divide by delta x, or dx, right? Remember, the derivative is the limit as delta x goes to 0 of the ratio of the difference of the function and the difference of the x points. So I need to define what dx is, and that's just x2 minus x1. So I have a uniform mesh, so the spacing between all my points is the same everywhere, so my dx is just a scalar. It doesn't vary depending on where I am on the mesh. Now if I do the backward difference, then I will subtract the present point minus the one in the negative x direction, which is referenced using the IW operator, so to the west. All right, so this is a finite difference approximation to the partial derivative with respect to x, and we can do the same thing in the y direction by just replacing the y's, the x's by y's. And of course, changing the I east with the I north, right? The point in the positive y direction, that's to the north, so we use IN, and if we want the one behind to the south is IS. So I'm assuming I'm facing north there when I point to the left and to the right. All right, so now I have two separate approximations for the x derivative and the y derivative. Oh, I forgot to change the names here, y and y. We can come up with yet a third approximation, and that one is a centered difference. And for that, to get it centered, we want the approximation to be not forward biased in the forward or in the backwards. We will take the point to the east and subtract the point to the west of us, so a point that's 2 delta x apart. Similarly, for the centered difference with respect to y, we'll take a point to the north and subtract the one to the south. So let's do the derivative with respect to y, x, the centered difference. So centered difference is going to be I east minus I west, then divide that by 2 dx, because these points are 2 dx apart. And similarly for centered finite difference approximation for y, I north minus I south, and divide by 2 dy. All right, so let's test these finite difference operators by creating a test function, which we're then going to differentiate analytically and then compare the finite difference approximation to see if we get the same answer, and by looking at the difference of the exact analytical answer and the approximate finite difference answer. So test function, and we're going to pick a function which is doubly periodic both in the x and in the y direction, because our shift operators have it built in implicitly that our fields are periodic in the x and in the y direction. So the analytical one, so first the test function f And to make it sure it's periodic, we're just going to take a product of signs. 2 star pi star x slash Lx. So that's periodic in x. And on the domain, it's sine 2 star pi star y slash Ly. Alright, and now if I wanted to do the derivative of partial derivative of this field with respect to x, the analytical answer is df dx subscript a is going to be derivative of sine is a cosine, 2 star pi star x slash Lx star the sine pi star y slash Ly. And then I also have to do the chain rule, the derivative of the argument of the sine with respect to x, so that'll give me a factor of 2 pi divided by Lx, 2 star pi slash Lx. Alright, and now we can also do the numerical approximation. So df dx numerical is just obtained by simply multiplying f dx with, so that's the forward difference with f. There's one more thing we need to do. So what the operator takes the 2D field f and converts it into a big 1D long vector. And so if we want the answer to be go back, so the output here would be a big long vector. If we wanted to go back to the 2D array of points, we will first initialize df dx n to be a 2D array of the same size as the mesh by simply setting it equal to x. And then we will overwrite those x values by populating it with the answer obtained from the finite difference. Okay, so let's make a plot and look at our answers. So figure 1, subplot 2, 1, 1. So in the first panel, we're going to show the exact answer. So contour f, x, y, df dx, analytical, put a color bar, and set the font size to be bigger so you can see it. The default Matlab font size is kind of small. Alright, and then we'll, in the second panel, we're going to plot the error or the difference between the analytical and numerical solution. So I have the analytical, subtract the numerical, and then plot that. Alright, let's try it, see if we have any coding errors. Okay, so this is the result. Let me stretch the mesh. The picture, I mean. So the top panel is the analytical derivative, and its size is between 2 and -2, the minimum maximum, whereas the error is between 0.01 and -0.01 roughly. So that's an error of 0.5%, right? Yeah, that's roughly less than 1% error. So that's pretty good. In this case, I have 500 by 400 points. We can try putting less points so that our mesh is bigger to see if the error gets worse. So let's do that. So if I try again, let me put some titles this time. Title, df dx analytical, and title error, and put some X labels. Alright, let's try again. So now we have, we've decreased the mesh size by a factor to, so our spacing is 10 times bigger than before. So we had errors that were less than 0.5%, 0.5%, and roughly, and let's see if they're... Alright, so now the error is of order maybe 5% this time, 5% error, right? It is of order 0.1, which would be, about 5% error. So before it was 0.5, so we have about an error that's a factor of 10 bigger when we made the mesh spacing a factor of 10 bigger. We can go the other way instead of, well, I think, yeah, we can go one more time. So let's pick 5,000 points and 4,000 points. So we used to have, when we had 500 and 400 points, the error was 0.5%. Now we've made the mesh, we have 10 times more points, so they're a factor of 10 smaller. So our error, if it goes linearly, we would get an error that's 0.05%. So let's try it out. All right, let's look at the error. So now the error is of order 10 to the minus 3. So that is indeed a factor of 10 smaller error. So it says if we divided the error by a factor of 10. So it does seem like these operators, the approximation, the error is decreasing linearly with the size of the mesh. So in fact, these forward and backward difference operators, these are known as first order difference operators. And that's in contrast to the centered ones. These are known as second order finite difference operators. And I'll put all the y's together, all the first order ones together and all the second order ones together. Now, what do we mean by first order and second order? That means that in these centered difference one, the error will decrease like a second power of the size of dx or dy. So we would expect a quadratic convergence rate. So as I go from 50 grid points to 500 grid points to 5,000 grid points, the error should decrease by a factor of 100, h factor of 10, so like 10 squared. So let's try it out, see if that works with the center difference. So I'll start with 50 points and 40 points. And over here, where I do the numerical one, I'll do the center difference approximation instead of the forward difference. All right, let's try it out. So clear all, gyre. Okay, so right away, a while ago, I had error of order 10 to the minus 3 when I went to the 5,000 points, although this is 5, it was 1. But I'm getting a relatively small error already when I only have 50 points. So this is a strong reason to use the center difference, these quadratic second order operators, because the errors decrease so much faster than the first order one. Let's double the resolution, or not double, increase the resolution by a factor of 10 by going to 500 points and 400 points. So we can make a prediction. If we think the error is going to decrease quadratically, we should expect the error here, which is of order 10 to the minus 3, to go down to order 10 to the minus 5 if our prediction, if the operator truly is quadratic. So let's try it out. Clear all, gyre. All right, here's the answer, and sure enough, now the error is of order 10 to the minus 5. So we've decreased the mesh by a factor of 10, and the error has decreased by a factor of 100, so divide by 100. And we can even go to the higher one to 5,000, just to convince you that it is indeed decreasing quadratically. Clear all, gyre. While that's calculating, we can go back to our code and change the code so we can do second derivatives. So these are all first derivative operators. We can get second derivatives by taking the product of these operators. So if we want a second derivative with respect to x, we can multiply by the FDX operator twice, or even better, we can multiply by the forward difference operator followed by the backwards difference operators, so that we will end up getting a centered second derivative, right? Because one is shifted to the right, is biased forward, the other one backwards. When we take the second derivative by mixing these two operators, we'll get a result that's centered at the coordinate point, and that's going to give us a second order accurate second derivative. And in fact, we're going to test this by constructing an operator for a Laplacian operator, which is the second derivative with respect to x plus the second derivative with respect to y. So Laplacian operator. And this is sometimes called del 2 or del squared, and it would be f dx times b dx plus f dy times b dy. So this is like a second derivative with respect to x plus a second derivative with respect to y. You notice we've mixed the forward and the backwards. That's to make sure that our del operator is a centered approximation. Let's see if our last calculation with 5,000 points is done. Yes. So sure enough, now the error is down to 10 to the minus 7, another factor of 100 less than it was when it was 10 to the minus 5. So we are indeed getting quadratic convergence to the centered, when we use a centered difference, finite difference approximation. Okay, so let's back to the Laplacian operator. We have this approximation. Now we will do the analytic derivative. So del 2 analytic, del 2 numerical, and del 2 numerical, and the del 2 numerical will be del 2. So that takes care of the second derivative numerical. We have to do the analytic one. So fortunately I picked functions that are easy to differentiate twice. If I do two derivatives of the sine function, I'll get back minus sine plus with the chain rule, the square of the factor of the x, plus I'll get a second derivative of sine will again give us a sine when I do the by dy. So in fact I get back a function that's proportional to f. I just have to multiply by the square of the factor. So let's type out the second derivative. So it will be minus 2 star pi slash lx squared minus 2 star pi slash ly squared, and all this multiplies back our original function. So it's easy to compute. So we have the analytical, the numerical, and now we can plot them. Del 2 and f analytical. I should put the f here. F, f, f. And then del 2 f analytical, del 2 f numerical. I think that's ready to try, but let's go back to a small number of grid points so we can see the convergence rate as we make the mesh finer and finer. All right, CLF, oops, gyro. All right, so oh, I forgot to change the title. Let me change the title. All right, so this is the analytical solution. So the answer is of order 10, between 10 and minus 10. And then the error is of order 2.5 times 10 to the minus 2 when I have 50 and 40 mesh points. Now I'm going to multiply or increase the number of mesh points by a factor of 10. So decrease the spacing by a factor of 10, or 1 over 10, and then run it again. So now the error is already down to 10 to the minus 4, so it seems to be again decreasing like the square of the grid spacing. Let's go to 5,000. And 4,000. So if we're going to make a prediction, we would expect the error now to go down to 10 to the minus 6 for this Laplacian approximation to my field. So it's 10 to the minus 4 now. I increased the number of grid points by a factor of 10, so the dx decreased by a factor of 10, and the dy's decreased by a factor of 10. So let's try it. While that's calculating, we can talk a little bit about doing the inverse operation. So if we take the derivative, the inverse you would think is integration, and with our operators, the analog of integrating is like inverting these linear operators. These are matrix operators. If we find the inverse of these matrices, it will be like doing the integral. Now, there's a catch, is that when we apply these finite difference operators to a constant field, right? If the field is constant, then when we subtract I times a constant minus IE times a constant, we will get 0. And indeed, when you take a derivative of a constant, you get 0. So that means if we try to undo the action of a derivative, we have no way of recovering what that constant of integration was. So if we differentiate 5, we get 0. If we differentiate 50, we also get 0. So if you're trying to invert that, there's no way of recovering the constant, and that's going to be manifested in the fact that none of these difference operator matrices are in fact invertible. They're all singular. You try to invert them, you will get nonsense. So that means that we have to go back to what we learned in calculus. When we do an integral, we get an integration constant, right? And when you forgot it and you were an undergrad, or when you were in high school, whenever you took calculus, you lost a grade because you forgot that the antiderivative, or the integral of x, is not 1/2 x squared, but 1/2 x squared plus c. Right? I remember missing it. My teacher would bonk me on the head with a ruler for missing the integration constant. I don't think teachers bonk students on the head anymore for missing the integration constants, but you know, it's a good way to learn it. You're on your toes and don't forget the integration constants. Anyways, that means that if we want our matrix operators to be invertible, to integrate, we have to somehow build in the integration constant, and we're going to do that by specifying boundary conditions on these operators, and to make them invertible, and to prescribe what these boundary conditions will be. So we'll do that next time. Alright, so presumably our calculation of the 5,000 points is done. Let's make sure. Okay, now it seems like it's done. Okay, so the error now is 10 to the minus 6, and I think last time it was 10 to the minus 4. So indeed, the error decreased by 2 orders of magnitude when we decrease the size of the mesh, the spacing between the mesh, by 1 order of magnitude. So it is indeed quadratic as predicted. Alright, so I hope you'll join me next time when we do integral operators by inverting these finite differences.